Where? You're gonna sign up for tomorrow, right?
Okay, here we go. So let's talk through some of these. Some of these we don't need to do, but let's at least talk strategies with them. So, gave you a function, find all the points on the graph at which the tangent line is horizontal. What would I do? Okay, find f prime of x. Well, we'll do this real quick. So what is f prime of x?
2x to the negative 1/2.
Okay, good, because we think of that square root of x. We think of the square root of x as an x to the 1/2. So the derivative would be 1/2 times 4 is 2, x to the minus 1/2. So we'll just put that square root on the bottom, right? There's the first term.
-2.
Minus 2. Okay, and if I want to know where the tangent lines are horizontal, what am I setting them equal to?
Zero.
0. Okay, that's the slope. Right, there's the slope function, and so I'm going to set that equal to 0 and solve for x, and that's how the math gods will tell me where the tangent lines are horizontal. So what would the steps be to solve for x here? Look like?
Add 2.
Add 2.
Divide by 2.
Okay, I could divide by 2.
Switch the x for the x.
So, okay, good. So I could just, the other thing I can do is I can transpose diagonal. Right? If I have a ratio, there's a 1 there, I can switch diagonal, right? That's just a real good shortcut. So the square root of x equals 1, so what's x?
1.
Okay, technically it's going to be plus or minus 1 if I square both sides, right?
But you can't have negative square root.
Actually, no, it's not. Never mind. It's just going to be 1. Never mind. It's not plus or minus 1. I just get 1. And I'd have to check that, okay, because quick review of solving radical equations. If I take both sides to a power, I have to always verify that the results work, because you can introduce extraneous solutions. So if I plug 1 in there, does it work?
Yes.
The original, it does.
Yeah.
Square root of 1 is 1, 2 over 1 minus 2 is 0. Okay. So how would I'm not going to do this one, but how would I solve part 2?
Say,
I would just set it equal to negative 3/2 instead of 0, right? And solve that. Okay? No big deal. Okay? Okay? You get that?
Yeah.
Okay, all right. Okay, so let's look at instantaneous rates of change versus average rates of change. Okay, so let's fill in this table. Tell me what you know. We'll just compare line by line what's similar, what's different. How do we define, how about, average rate of change?
secant
Okay, it's the slope of the secant line, right? So the average rate of change is equal to the slope of the secant line. What's the instantaneous rate of change?
tangent line.
Slope of a tangent line. Okay, the average rate of change. The average rate of change is given by what? What's the definition? So we could call that like, let's call it delta y over delta x is one way to say it. I'm using deltas instead of d's because they're macroscopic. But how do we calculate an average rate of change for a function? So it's the slope of a secant line. What is that? Okay, change in y over change in x. Good. What is that in terms of like f? F of there you go. Good. Good. And you're thinking pictures, right? You're thinking the picture that we drew with the 2 points that define the difference quotient, right? Always think in terms of pictures. You won't forget that. So f of x plus delta x minus f of x over delta x. That's it, right? Okay. The slope of a tangent line, that's dy dx. Or if we want to call it f prime of x, we can do that. But what's that definition? What do we have to do to the secant line to make it a tangent line? Take the limit. The limit of the difference quotient as delta x goes to 0, right? Okay, so, I mean, that sums it up pretty well. So an average rate of change is gonna be over an interval, an instantaneous rate of change is at an instant, right? It's at one moment in time on the curve, okay? We might come back to this and add some other stuff later, but those are the highlights. Okay, so let's look at some problems then. So let's do, okay, here, this is a good one, yeah. Write the area A of an equilateral triangle as a function of the side length S. Now, first of all, I like that. Right there, that's a pretty good question. That's asking you to do something that's not trivial. I mean, it's not hard, but it's not something, you don't have a formula for that problem yet. But you might remember, but you probably don't. Does anybody remember?
You're going to take S to the square root of 3 times S.
Kind of. I mean, you're on the sort of the right track. You're inching closer to the solution, but this is something that I would never. Yeah, I actually probably do remember this, but I'm not sure if I'm right. So I would always just solve it for myself, because it's that you never go wrong if you just remember how to derive something quickly for yourself. If you memorize individual facts, you just forget. I have. I used to know all the state capitals. Now I know like 3. So. If we have an equilateral triangle, right, what's that mean? All the sides are length equal. They call them S. So if that's S, well, how are we going to come up with the area of a triangle? What's the one formula for the area of a triangle that you definitely remember? Half the base times the height, right? So we know that the area, if it's half the base times the height, well, that's going to be 1/2, what's the base? S, times the height. Okay, so if that's the height, we'll call that H. What can you tell me about the length of that side right there? Well, no, that's just S over 2, right? Because that's half of, did everybody agree? That's a right angle. So if I want to find the height, this is pretty easy, right? Just Pythagorean theorem, right? H squared plus S over 2 squared equals S squared, right? So H squared plus S squared over 4 equals S squared. So what's H squared equal to? Minus 1/4 S squared is
3/4 S squared.
3/4 S squared, right? 1 minus 1/4 is 3/4. So then what would H be if I solve for H?
H.
I'm just going to square root both sides, right?
Yeah.
And what's that going to give me? So I'm going to get square root of 3 over square root of 4. Well, that's square root of 3 over 2. S, and technically it's plus or minus, but this is geometrical. There's no such thing as a negative height, right? So we'll just take the positive one. So there's the height. So all I got to do now is just plug that in for H, and we get 1/2 S times the square root of 3 over 2S is what?
S squared.
Square root of 3
Over 4.
S.
S squared.
There you go. So there's your formula, and now you probably remember it. I mean, I remember that, but I don't know. A couple of years, if I didn't teach calculus every year, I would forget that within a couple of years for sure. So square root of 3 over 4S squared. So that helps. We got part A, right? We found the instantaneous rate of change of A with respect to side S. So there's part A. Okay, now how about part B? Find the instantaneous rate of change of A with respect to area A with respect to side S. So what is that? The rate of change of A with respect to S, what does that mean in terms of calculus? It indicates the slope of a tangent, right? If we were to graph it, that's a great way to think about it. You always want to think about this stuff in terms of what a graph would look like. If I were going to graph area, I would graph area on the vertical axis and side length on the horizontal axis, right? And that's the function we would get. It would do something like that. And so if I pick a value of S, like in this case 6, it's the slope of a tangent line. Okay. Do you really have to build that whole thing up? No, it can be useful, but you can always just equate a rate with the derivative, right? If they're talking about a rate of change of area with respect to S, that's just dA ds. That's all that is, right? So automatically, when you see something like this, rate of change of A with respect to S, that is, either think of it as dA ds, and I know I'm stating the obvious here, but I just want to point this out. Obviously, if it's the rate of change of area with respect to something else, that means that goes on the bottom, right? Okay. So dA ds, if I use a different notation, I could write it as A prime of S. Either way, this is A of S, isn't it?
Yes.
Right? That's area as a function of side length. So what's its derivative? It's pretty easy. There it is. There's my derivative function, right? And so for part B, what they're asking us to find is, oh, that's it, okay? Evaluate the rate of change of A at S equals 1 and S equals 6. So for part C, at 1, I would just be calculating A prime of 1. What's that? Square root of 3 over 2. Okay. At 6, I would be calculating A prime of 6, which is, okay. Make sense? Okay, what do those mean, though? What's that mean? What is A prime of 1? If it's equal to the square root of 3 over 2,
When the side lengths are 1, the area is square root of 2.
so let me repeat that, and you tell me if this sounds right. When the side length is 1, the area is the square root of 3 over 2? No, it's not, because that's what, we didn't need calculus for that. That's what the area function did for us, right? The area function is telling us for a given side length, it's telling us area, right? This is telling us something different. What's it telling us? Okay, so how rapidly the area is increasing at that particular value, right? So does that mean, like, if I were going to take my side length and go from S equals 1 to S equals 2, that it would increase by square root of 3 over 2? No, it doesn't. It doesn't actually, right? It's difficult to kind of conceptualize this, but an instantaneous rate of change has nothing to do with any interval. It's telling you at that exact instant, that's quantifying how fast the area function is growing, right? The best way to think about this by far is speed, because you do it all the time. In your car, and I know I've talked about this, but I'm going to say it again in this context. Think about what a speedometer does in your car. Right, a speedometer tells you if you're speeding up and your speedometer, at the instant your speedometer says 60, that has nothing to do with how far you're going to travel in the next moment of time. 0, right? It gets you in the ballpark, but all it's telling you is at that one instant in time, that's telling me how fast the road is going by if I look out the window, right? I might smash into a wall in the next second and I'm not going anywhere, right? But my speed, when I looked at the speedometer, my instantaneous speed was still 60 miles an hour, right? It has nothing to do with the time before it or the time after it, regardless of how close you get in time. It's at that one exact instant. That is a number we can apply to that rate of change. Does that make sense? Okay. That's completely different than an average rate of change. If we wanted to figure out, well, let's look at another example.
So what is it in that?
Say it again.
What is it in that context?
So in this context,
Yeah.
so that gives us a number value. So the fact that this one is the square root of 3 over 2, right? So what is that? 1.8, who knows? Some decimal, right? Some decimal. 0.707, something like that. 7071, something like that. So it's just some decimal value. Down here, it's a lot bigger than that, right? This is a number that's considerably bigger than 3, right? So this just gives us a basis of comparison. It's telling us that here the area function is increasing a lot faster than it is here, right? It just quantifies that. That's all it does. Okay. What does 60 miles per hour tell us? Twice as fast as 30 miles per hour, right? If we were to hold that speed, then it's predictive. Then we could say, okay, if I put my cruise on, well, then I know I'm going 60 miles in the next hour, right? But the instantaneous rate has nothing to do with that. It's telling me at that instant, how dangerous would it be to crash into a wall, for example, right? It's telling me the speed I have is proportional to, the energy is proportional to the square of that speed, and so that's an important thing to know, right? Having that number is important. Okay? But that's all it is an instantaneous rate. How about something like this? Oh, actually, I just did one like that.
Yeah. Can we do that one?
Oh, this is a pretty good one, though.
I have.
Actually, this is a pretty good one. There's something else about this one. I know why I picked this one. Pretty good one here, too. So the area of a circle as a function of circumference. Okay, this is one where you guys know the equations that would play into this. What's the area of a circle? What's the formula you know? Area is equal to pi r squared, right? You know it in terms of radius. Okay, well, what's circumference? 2 pi r. So how am I going to write area as a function of circumference?
U of the R over the set.
What do you mean by that?
So there's. Wait.
This is a really important question. This helps you out on a lot of jams in math. It's just no simple
Pi
strategy.
times 2 pi parentheses 2 pi r squared. Right?
No, you're making this too hard. There's a really simple way to do this. I've got two different equations, and they share a common variable, right?
Solve for.
Hi.
Good. You do a substitution equation. So all you have to do is isolate r in this equation and substitute into this one. You see that? So if we isolate r here, r equals c over 2 pi. That's what we call our substitution equation, because we've isolated the variable we want to get rid of, right, in favor of c. You see that? I've got r's over here and I want c's, so I got to find a way to trade my r's for some number of c's, right? That's how we do it. You isolate the variable you want to get rid of and substitute that one. So we'll plug that in right there, and we end up with a of c equals pi times r, which is that quantity, c over 2 pi squared. Right? So what's that work out to be? Pi times, what is that quantity squared? C squared over 4 pi squared. I can cancel a pi, and I get a of capital C equals c squared over 4 pi, right? So now I've got area as a function of circumference, okay? So if I wanted to find the instantaneous rate of change of area with respect to circumference, what would that be? Derivative. Derivative of what with respect to what? Area with respect to circumference. Good. So we're asking about dA, dC. Another way of writing that would be what? If I use function notation. Okay? Right? What's that give us? Everybody agree? Bring the 2 down, cancels with 4. Okay, there's our function. And then the rest of it's pretty trivial. If we want to evaluate the rate of change of A with C, I've got 2 values I could plug in and see what we get. Right? So what about this? Annual inventory cost C for a certain manufacturer is given to us by this function. Some quantitative economist has fit some data and come up with this equation. Right? So based on where Q is the order size when the inventory is replenished, find the change in annual cost when Q is increased from 350 to 351. Okay? Is that an average or an instantaneous rate they're asking about? That's an average, isn't it? Right? Everybody see that? Okay, because we're talking about an interval where Q is running from 350 to 351. Okay, so the average rate of change of Q with respect to, of C with respect to Q, right? So we could call that delta C over delta Q, right? Change in C over change in Q is just what? Don't give me an answer yet. How would I write that? C of what number? $351 minus C of over, well, 351 minus 350, which is 1, right? And so what's that give us? If I evaluate this at 351, that's getting pretty ugly. That's yikes. So that one right there is going to give me, that one's going to be 1,008,000 over 351. I don't know. You get the idea, right?
Yes.
I mean, I'm just going to get some number here minus some number there divided by 1. Right.
Just like,
Yeah.
finding 2 points like students do.
That's all it is, right? That's all we're doing. So if I were to graph this thing, this is just the slope of the secant line connecting. And what would the, we don't have to graph the whole thing, but you always want to think in terms of what a graph would look like. What is going to be the space in which this would be graphed? What would go on the horizontal axis? What's the input variable? Q, right? So we're going to be measuring Q on this axis, and what on the vertical axis? C, right? And I'm just going to have an inverse function. It's going to be doing, oh boy, it's going to be doing some weird stuff. So it's going to be going like that, it looks like. But anyway, that's regardless of what it looks like, that's what we're looking at, a rate of change of that function. So there's going to be two points connecting that curve, which is just doing something like that, I guess, somewhere. And so here are the 2 points, and we're finding a slope of the secant line. Okay. Okay. Compare that with the instantaneous rate of change when Q is 350. Okay. Let's just do this real quick. This is a prime opportunity to use like Desmos. Desmos makes this really simple. Does a lot of work for us. So you guys know how to use Desmos to do this, because this is okay. Well, let's talk about that, because this is a tool that you will use a lot in college. I would have loved to have this in college. So let's define our function C of Q. Can't type. There we go. C of Q equals 1,008,000 divided by Q plus 6.3 Q. And then we can just come down here and do, just do the expression C of 351 minus C of 350, 350 divided by 351 minus 350, and it gives us that value, negative 1.905, blah, blah, blah. Okay? So let's find the derivative, and we'll come back to that. So let's come up with our derivative functions. So if that's C of Q, what's C prime of Q?
Negative that number. 2 negative 2.
So I've got, how do I, now this, do I want to use quotient rule here? Oh, we haven't talked quotient, never mind. Sorry, that's tomorrow. That's tomorrow. Sorry, that probably caused stress. How do we rewrite this so we can use our power rule here? What's the exponent? Q to the negative 1. So this is just equal to 1,008,000 Q to the minus 1 plus 6.3 Q. So what's the derivative of that?
Negative 1,000.
Good.
Plus 6.3.
Plus 6.3. So what I mean, this is just my little here, right? Yes, I like to do this. I like to do. I want to put the positive term first. Okay, so there's our derivative. Question?
So on that, so.
Say it again.
On that Excel.
No. Oh, no, it doesn't matter. Either way is fine. Yeah, shouldn't make any difference. What?
It does allow spurs on the bottom of this.
And they use the
Yeah.
wrong variable. That costs you some problems too.
Show me that one. I want to try to fix that one. That's not supposed to be that. That's an error. Okay, so then we've got C prime. We'll just call that F. F of Q equals, what was this? 6.3 minus 1,008,000 divided by Q squared. And we just want to evaluate that derivative function that we called F at 350. And look what we get. We get something a little bit different, right? Okay, so make a prediction for me. I want you just to use reasoning here. So if the value of the derivative at 350 is negative 1.928, blah, 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 so a little bit less than, a little bit, right? It's a number that's less than the average rate of change. What do you predict is going to happen if I evaluate the derivative at 351? It'd probably be a little bit greater, isn't it? Right? Because the average is likely to be somewhere in between, unless the function's just zipping all around and doing weird things. But it's probably not, right, on that small a scale. So the odds are, if we do f of 351, sure enough, look what we see, negative 1.88. So it's slightly greater than negative 1.905, right? And the average is, as you'd expect, it's going to be somewhere in the middle. Okay? Is it exactly in the middle? No, because the function's not linear, right? It's curving. Okay, okay, so how are we doing for time here? 14. Okay, so you got a little time. So let's, question.
Not a question, just a comment.
What's that?
Not about this.
Okay. Okay. So let's kind of try to organize the little talk we had about kinematics too, right? So kinematics, study of motion, right? Kinematics is, if you're in physics, you've said this word lots of times. So kinematics is going to be, we're going to study the relationships between position, velocity, and acceleration, right? And then time, right? With time, we're going to look at how those quantities change. Okay, so position is what we call a vector quantity. And that's going to be S of t, right? Position's a vector quantity because it has both a magnitude and a direction. And the example we used, if we look at motion along a straight line up here, where this is 0, this is positive 1, this is negative 1, well, the negative and the positive mean something, right? They're telling us if that's the positive direction, positive 2 means it's 2 greater than 0, that means 2 to the right, right? A position of negative 1 means it's 1 less than 0, so it's got to be 1 to the left on this line, right? Okay. What's the scalar that goes with that? With position? Yeah, it's absolute value. It's kind of a weird thing, but I guess we're talking about a distance thing, right? A lot of times, I think you guys do this in physics. I want to relate this to what you're doing in physics a little bit, so you can tie this into what you're doing in physics. You guys mostly, I think, don't you? The book you're using, do you write your equations in terms of displacement instead of, okay. So then displacement is related to position. Think what that means. Displacement is just going to be change in position. That's all that is. Displacement is equal to delta S. Okay, and a lot of times you'll put a little vector hat over the variable that's a vector just to really point out that it's a vector. Sometimes in textbooks they'll make them bold-faced, but usually they'll put a little vector hat. So change in position just means final position we'll call that S of t minus S of 0, wherever you started with, right? Whatever your starting position was, whatever you end up, minus that. So for example, if I start at -1 and I end up at +3 or +2, what's my displacement? +2 minus -1 is 3. Okay, that makes sense? Okay. What if I start at -1 and I walk out to +2 and then I walk back again to here? What's my displacement? Okay, but displacement has nothing to do with, all it has to do with is final position and initial position. So it's 2, right? If I start here and I walk all the way out here and I walk all the way back, my displacement is 0. Okay, all right. So displacement is a vector quantity, right? We're talking about change in position. The scalar equivalent of that is distance, right? Distance is not a vector. Distance is always positive, right? We're talking about a distance. I could say something like, if I start at +1 and I end up at -1, my displacement is actually -2. Why is that? What did displacement describe? Where I started and where I ended. My net movement was 2 in the negative direction, hence the negative sign on displacement. What's my distance? 2. Hey, you wouldn't go out and say, if you ask somebody how far they ran, you're not asking them a vector question. It's kind of silly to say, I went out and ran -3 miles. That's pretty good. It just doesn't make a lot of sense, right? You're asking them a distance question. Okay, so what about, next level down is velocity. Okay, so velocity usually we call it v of t. What's the relationship between velocity and displacement? That's important. Velocity is what? Oh, okay, now that's average velocity, right? And that's different. We can do that. Let's talk about them both. Average velocity, which is what you guys are stuck talking about because it's not a calculus-based physics class. Average velocity, which we call delta, actually we just call v bar, typically. V bar, bar means average, is just displacement over time. That's all that is. That's just going to be change in position over change in time. What's that look like to you? If I were graphing this, what would that look like? If I were graphing, it would, wouldn't it? If I were graphing position versus time, and I had some function, and I'm going to say that's, well, there's one time, call it t1, and there's t2, and I want to measure an average velocity between those. Look what that is, right? That's just the slope of the secant line. So change in position over change in time, right? Okay. But when we talk about velocity, we're implying instantaneous velocity, right? This is calculus stuff, right? So what's instantaneous velocity? And this is like next level compared to what you're doing in physics, because yeah, you guys can't do this, but we can here. So if the slope of the secant line is the average, what must the instantaneous rate be? Slope of a tangent line. What's that sound like? Slope of a tangent line always goes with. Okay, that sounds like an awful lot like a derivative, doesn't it? This is a rate. The rate of velocity is the rate of change. Instantaneous velocity is the instantaneous rate of change of position, right? So that is ds dt, which is s prime of t. Okay, so we're taking, that's giving us something arguably more important, right? Instantaneous rate of change. Now, what's the scalar that goes with that? Instantaneous speed. How is instantaneous speed related to instantaneous velocity? It's the same magnitude, just doesn't have a sign attached to it, right? So if I'm walking in this direction, in the negative direction, and I'm covering 2 meters every second, take your pick of instance when I was walking there, at any of them, my velocity, my instantaneous velocity was 2 meters per second, negative 2 meters per second, because I was moving in the negative direction, right? What was my speed? 2 meters per second, right? Okay. All right, we could go, okay, this is something that I'm definitely going to talk more about this. What if we did, what's the scalar equivalent of average velocity? Okay, so let's try this. If this gets a little trickier. So I'm going to start at -1, and I'm going to walk out to +2, and I'm going to walk back to here over a course of 5 seconds to 0. What's my average speed?
1/5.
Okay, if I want it, now you got to be careful about this because there's a couple ways you can slice this. If I want to know what was the total distance I covered, right, divided by the time, I actually walked a total distance of 5 meters, didn't I? Divided by 5 seconds would be 1 meter per second. Okay, right? What's my average velocity? Started at -1, ended at 0, took 5 seconds. 1/5 of a meter per second, right? These are different things, aren't they, right? If I were, go ahead,
When
question?
you calculate scalar quantities, can you only use scalar values?
What do you mean by that?
So like when you calculated your average speed, you use distance. But when you calculated average velocity, you use displacement.
Okay, so the answer is there's two different answers to the question. I was trying to be a little tricky there. There's two different answers to the question average speed. You could be asking for what is the total distance you walked, or you could also be asking what's the magnitude of average velocity, right? And either way, they could be different, because if I started here and ended here, my average velocity would have been negative, but my average speed would have been positive. But like what you would potentially see on the AP test would be a tricky question, would be to say something like, what's the total distance covered? And then what was the average walking speed during that period? And so that's going to be something where you're going to take the total distance that you've traveled and divide that by the total time. So in this case, we walked 5 meters in 5 seconds, and so we got an answer of 1 meter per second, whereas the average velocity was only 1/5, right? That's a question that we're going to have much better tools to answer questions like that in the future. So I'm not going to belabor that point too much now. I just wanted to mention it so you're aware of it, right? Okay, last thing on here, and then we'll be done with this. So what's the next level then? So velocity is the rate of change of position with respect to time. What's acceleration? Instantaneous. So we're talking A of t. What's that equal to? The rate of change of velocity with respect to time, right? So that's dv dt, which is the same thing as v prime of t. Okay, what is that in terms of position? This is a new concept. Yeah, you're taking, this is kind of weird, you're taking the derivative with respect to t, and we're going to change this notation, of the derivative of s with respect to t. So it's the derivative of a derivative, right? Velocity is defined as a derivative, and acceleration is the derivative of velocity. So the notation for that is pretty bizarre, but here's how we write that. A of t equals d squared s over dt squared. I never write it that way. I gotta look at that in the book real quick. D squared, I'm pretty sure that's right. D squared, that's right. You almost always write it with, yeah, but you might see it this way. So I want you to be aware of it. Higher order derivatives, there we go. Yeah, d squared, right. So it'd be d squared S over dt squared. Oh, for a line, if we're using y's and x's, you would write it as d squared y over dx squared, right? That's one way to say it. A much better way would just be s double prime of t. 2 primes for 2 layers of derivatives. Okay?
Got
Make sense? Okay. We out of here in 1 minute?
30 seconds.
30 seconds.
I talked to Miss Sandman this
Yes.
morning, and she said, we can have that room on Tuesdays and Thursdays. She said she has no problem with it. She said if we want to go there Tuesdays and Thursdays, she'll have like Michelle request all the, but she wants to do it for like AP Lit students and AP Calc students, just to study hall basically for all the AP students. I know, you have some Tuesdays, I'm telling it. And, okay, we'll figure that out. But Michelle will request everyone in room 203, and she said if you don't want to come, you don't have to, but we can use the whiteboards and the tables and stuff.
So what does Elton have on Go.
So then, how about if I'll pick you guys obviously a different day then. Why don't we set like either you pick like Wednesdays or Fridays?
I'd say Wednesdays, so that
Wednesdays.
we can
Wednesdays.
get questions from you and then work on.
And
Perfect.
sports are usually gone.
Okay, so I'll plan on Wednesdays then. I'll just get calc students on Wednesdays.
Well, this is exciting. Wow, the Calculus Club is really coming together.
It is. Isn't the calculus club coming together?
But she said she's